Hi, hello, good evening, everyone. Welcome to week 8 of Fuzzy Sets Logic and Systems and Applications. I'm your teaching assistant. My name is Pravalika Saladi. I'm a PhD scholar and a Prime Minister Research Fellow from IISc Bangalore. So, as usual, let's go through our instructions before we begin the class. So, this session is being recorded, and please put all your questions in the chat box during the session, and I'll be answering them to you. Okay. So last week we have looked at fuzzy relations and other operations relevant to it. So this week we are looking at fuzzy relations, but in a quite different context. This is called as an composition operators. Okay, there are different strategies that we follow to find this fuzzy relations. Okay, so let us say that we have three space. Okay, let's say X, Y, and Z. So uh, when we take a relation, let us say we have one relation between X and Y, and let's call that as R1. So these relations here between X and Y, we are calling this as R1. And the relations between Y and Z, these are R2. Okay. So we have two sets of relation, but if at all, I want to know the relation between X and Z, then how do I calculate it? Okay, so to calculate the relation between two uh, two spaces when another space is also involved in this way, right? So how do you do it? For that, we follow two different type of strategies. One is maximum composition, another one is max product composition. Okay, let us say R1 is the relation between X and Y, and R2 is the relation between Y and Z. So in order to get the composition between R1 and R2, we represent it as X comma Z because tentatively at the end we want to uh, get the relation between X and Z, right? The space X and Z. So X comma Z, and the membership value is going to be R1 O R2 X comma Z. So this O is nothing but composition output. Okay. So I hope till here it's clear. Okay. But now you have to know how to calculate this membership function for two given relations R1 and R2, right? So the first one is maximum composition. So it is given by this. So which means you first you take the minimum of R1, new R1, new R2. So new R1 with respect to X and Y and new R2 with respect to Y and Z. Okay, both the Y values should be the same here. Okay. First, you take the minimum value of that. For I hope you all remember. So we'll see an example. How do we take this minimum and then how do we take the maximum? It is based on the relation matrix that we calculate when two relations are given. When we have the relation matrix, so we take the minimum values um, from both the relation matrix that we are going to have because from R1 we are going to have one relation matrix and from R2 we are going to have another relation matrix. So we take one element from here, one element from here. We take the minimum of it. Like that, we'll have multiple elements with respect to one y1 value or y2 value. And out of all of those y, we take the maximum. So to sum it all up, it's nothing but max max for a given y, max in y, and minimum of the membership values. We you will understand it once we start with some example. Okay, if you are kind of confused right now, it's still okay. Okay, right. So we when we have this relation matrix, two relation matrix, I hope you all remember how we do matrix multiplications, right? Just as an example, let us say we have two matrices like this. So first we take one row from one matrix and one column from the other. You multiply this with this, and then you add them up, right? Similarly, AE plus BG and then AF plus BH. Like that you get one here, one here. So this is your usual matrix multiplication. But when you are dealing with a relation matrix for this maximum composition, instead of multiplication, you take an intersection. Instead of summation, you take the union, right? Intersection means we take the minimum, and union means we take the maximum. Okay. So we'll understand that when we take an example and we'll see how to calculate this. Okay. So now, okay, we have R1 relation, we have R2 relation. Let us say, for example, for R1, we have 3 cross 4, and for R2, we have 4 cross 2. One thing is that this is X, this is Y, this is Y, this is Z, right? So, one main thing that you have to follow is that the values of these two should be the same. So, the Y values should be the same. The relation matrix which we are taking, in that the Y value should be the same. So similar to how we do the matrix multiplication, right? So let us say I have, okay, M cross N as one matrix, let us say A, and another one is N cross T, right? The resultant will give us M cross T. This and this should be the same, and this is going to be the result, right? So similarly, even for composition of two relation matrix that we take, this 4 and 4 should be the same. So that is the Y value should be the same, and the output is going to be 3 cross 2. The so when we take a composition between two relation matrix, at the end we are going to end up with one relation matrix, and that is going to be 3 cross 2, like this. That is going to be another relation matrix of the size this. Okay, so far clear? So far is everything clear? Any questions so far before I get into the examples? Okay, so okay, let's continue with some examples. Okay, now here in this example, I have two relation matrix R1, R2, and R1 has three X generic the generic variables X1, X2, X3, and Y1, Y2, Y3, Y4. So four variables we have in Y. And in R2, again, we have four values of Y and two values of Z. Okay. So first, let us write the shape of it. R1 is in the shape of 3 cross 4. R2 is in the shape of 4 cross 2. So the resultant R1 O R2, the composition of R1 and R2 is going to be 3 cross 2. Right? Okay. Till here, it is clear for us. Now, let us do some sort of a matrix multiplication kind, right? So first you take one row and then you take one column. It is usually 0.1 cross 0.1. But as I said, instead of cross, we are going to take intersection, right? 0.1 intersection 0.1 plus 0.9 intersection 0.5 plus, sorry, it's not plus, it is going to be union, right? In place of plus, we are writing union. In place of multiplication, we are writing intersection. Okay. So 0.9 intersection 0.5 union, 0.6 intersection 0.3 union, 0.4 intersection 0.8. Is it clear how I got these values? Okay. So 0.1 intersection 0.1 is nothing but 0.1, right? Union. 0.9 intersection 0.95 is 0.5. So intersection means we take the minimum value, right? Union 0.6, 0.3, 0.3. Union 0.4, 0.8, 0.4. So union here indicates the maximum value. So it's basically nothing but max of 0.1, 0.5, 0.3, 0.4, right? So the maximum value is 0.5. So this is with respect to x1 for all y's and z1 for all y's. So x1 comma z1, the membership of x1 comma z1 is equal to 0.5. So the same process you have to repeat for the second row and the first column, the third row and the first column, and again first row and the second column, second row, second column, third row, second column. So like that you do multiple things and then you end up with 3 cross 2, right? You're going to end up with x1, x2, x3, z1, z2. So for now we have got this value as 0.5. So similar to how we have done this, you have to do for other variables as well. And then you'll get x1, z2, x2, x2, z1, x2, z2, x3, z1, and x3, z2. So you'll get a total of 6 elements of the shape 3 cross 2. Right? So far clear? Okay. So just solve for the rest. Okay, so this is one example of like random values that I have taken. If you can see, it's 0.1, 0.2, 0.3. It's like line numbers. Okay. So you can try it out yourselves and do let me know what answers you have got in the next class. Okay, so that is one question. So another question I have given here. So here I have two relation matrix R and S. Okay, and for one is from the space 1, 2, 3, which is basically integers, and another one is alphabets A, B, C, D, right? And in S relation also we have A, B, C, D, and the other one are alpha, beta, and gamma. So this is of size 3 cross 4. This is of size 4 cross 3. So the resultant ROS is going to be 3 cross 3. Right? So you again follow the same procedure that we have followed at the top. It's almost like a matrix multiplication. So you take the first row from R and you take the first column from S, and you, when in place of multiplication, you put an intersection, and in place of addition, you put a union, and then you will get one membership value for one particular thing, right? Okay. So this is going to be of the shape alpha, beta, gamma, and 1, 2, 3, which is a 3 cross 3 size. So this is our relation matrix. And in the previous problem, this is a relation matrix between X and Z, right? X and Z. So we had R1 from X and Y. We had R2 for Y and Z, but we don't have a relation between X and Z. So in order to get that, we have followed this whole Maxwell composition, and then finally we have got the relation matrix between X and Z, right? Okay. So similarly, try to do this. I'll give some time. Maybe I'll just wait till 6:25. Okay. I hope you finish this matrix here. Is that all right? I'll just mute myself for a minute. So let's wait till 6:25 and then check if we have got the right answers or not. Okay. Great, Janani. So, really good. Okay, I'm just going with Janani's answer for now. Okay. So, okay, let's just check for one or two. Okay, the first one is 0.1 intersection 0.9. So let's just take right max out. 0.2 intersection 0.2, 0.0 intersection 0.8, 1.0 intersection 0.4. Okay? So it's going to be max of 0.1, comma 0.2, comma 0.0, comma 0.4, which is equal to 0.4. Yes. Okay, so this is for the first one, which is with respect to R value 1, and for S, it is alpha. Right? So 1 and alpha is 0. The membership value of 1 and alpha is 0.4. Right. So let's do for one more and then we'll go with Janani's answer. Okay. Nice. So 0.1 intersection 0.0 is max of 0.2 intersection 1.0, 0.0 intersection 0.0, and 1.0 intersection 0.2. That is equal to max of 0.0, comma 0.2, comma 0.0, comma 0.2. So which is equal to 0.2. And this is with respect to 1 and beta, right? So this is going to be 0.2. So I'm going with Janani's answer. Okay, 0.4, 0.3, 0.3, 0.3, 0.8, 0.8, 0.9, 0.8. Great, Yamuna. But the first element is wrong. The first element is 0.4. Okay. But rest all you have got it right. Okay. Yes. Okay. So that is all for max and min composition. So in place of min, now if we are going to take a product, then it's going to be max product composition. Right? So the entire procedure is going to be the same, except for the fact that instead of using intersection, we are going to use multiplication. Okay, but every other thing is going to be the same. So for the membership value of R1 or R2 for x comma z, it's going to be max in y and new R1 multiplied by new R2, where R1 lies in x is the relation between x and y, and R2 is the relation between y and z. Okay. Okay. So let's do a quick example from here, the same one. I know it's a bit messy, but please bear with me. Okay, the same example I'm taking over here again. And the same example I'm taking over, but let's just do it. Okay, so we'll take the first. Let's do it with a different color. Let's take the first row in R1 and first column in R2, right? It is 0.1 multiplied by 0.1, comma, 0.9 multiplied by 0.5, comma, 0.6 multiplied by 0.3, comma 0.4 multiplied by 0.8. Okay, and max of these values. Right? So max of 0.01, comma 0.45, comma 0.18, comma 0.32. Right? So what is the maximum value here? The max is 0.45. Right? So when we take R1 and R2, let us say the relation is R between x comma z. Okay? We have the relation matrix, and the relation matrix is, sorry, x z1 z2 x1, x2, x3. And the first value that we got is 0.45. So in the similar manner, you also find other membership values with respect to the generic variable x and generic variable z, and then you finally get your answers. Okay, so this is for max product composition. So do it yourself from here. Okay, it's not complicated. It's a simple math, right? But in case if you do have questions, so I'll just finish up the whole class early. Okay, if you can try it out meanwhile, and if you do have questions, we'll try and solve it together at the end. Okay, good. So, so we have so far covered maximum composition. We have covered max product composition. Now we are going to look at fuzzy tolerance relation. So this fuzzy tolerance relation is a relation between their own space. So if we have X, we are again going to take X. So it's the relation here is more like, okay, if I say this is the X, the space, I'm going to find the relation again on the same thing. Okay. So it's like self relation. What is the relation between X and X? Okay. So in order to call this as a fuzzy tolerance relation, you have to follow two conditions. Okay. The first one is reflexivity. So reflexivity means for for the given for the same elements, sorry, for the elements, okay, let us say we have, how do we usually write a matrix? We write the row value, the column value, and then row value, column value, row value, column value, and then again row value, column value, row value, column value, row, column, row, column, row, column, row, and column. So this is how you usually write a matrix, right? But if I want to write this in a simple manner, I can write it as, okay, xij for all I comma j equal to 1, 2, and 3. Okay, I can represent each element here as xij, right? And I values range from 1 to 3 and j value range from 1 to 3. Similarly, if I'm saying I need values like xi, I, xii, which means both the values should be same. So what all elements will come under this? X11, X22, X33, right? Which are nothing but X11, X22, X33. So all the diagonal values we are getting, all the diagonal elements we are getting, right? So similarly, here reflexivity means all the diagonal values in the relation matrix that you are given should be equal to 1. Okay, so that is called as reflexivity. Okay, so that is the first condition. The second condition is symmetry. So all values of xij should be equal to xj comma xi. So it's like x12, x21. These both values should be the same. x31, x13. These both values should be the same. And x32 and x23. These two values should be the same. Right? So when the values are similar like this, then we call it as a symmetry. Okay. So again, I'm repeating. To say that a relation matrix is a fuzzy tolerance relation, then you need to follow two conditions. One is reflexivity, which means all the diagonal elements in the relation matrix should be equal to 1. And the other one is symmetry, right? So the symmetry is the membership value with respect to xi and xj. It should be equal to the membership value with respect to xj comma xi. Okay, so here is an example. So first with respect to reflexivity, before I said relativity, I'm sorry for that, it's reflexivity. Uh, with respect to reflexivity, So for this given example, the diagonal values are equal to 1, right? And hence this is sorted for us. So this condition is satisfied. So the next one is we have to look for symmetry. So here we have only two options, only two pairs, x11, x22, x21, and x12, right? So this is gone under reflexivity. But for symmetry, we are only looking at x21 and x12 because that's the only pair which is possible for this given matrix. So x21 is 0.9 and x12 is also 0.9. So both of them are equal. So it is a symmetry as well. All right. So, so that is for reflexivity and symmetry. Here are some examples. Let's do these examples and see if these are fuzzy tolerance relations or not. Okay. So for the first one, ref reflexivity. So here the diagonal elements are these. Oh, this, 2, 3, and 4. Right? So these values are not equal to 1. And first and foremost thing, it's not even a square matrix, right? So this itself is not a relation matrix of x cross x. It's not a self-relation that is for x cross x, right? It's not. So reflexivity is not satisfied and symmetry also will not be satisfied. So now let's look at this O. Okay. So it's a square matrix, well and good. Then we'll look at this. So we have all zeros for the diagonal matrix, and hence the reflexivity is not satisfied. Is not satisfied. So O is not a FTR, it is fuzzy tolerance relation. Okay. So let us look at E. So E, we have all the diagonal values to be 1. Yes. So for E, reflexivity is satisfied, and then symmetry. So value of 2, sorry, 2, 1, 2 and value of 2, 1 are equal. Value of 1, 3 and 3, 1 and 3, 1. Value of 1, 4 and 4, 1. So all of them are same, right? All the pairs are equal. So the symmetry is also satisfied. Okay. So E so far is an FTR for us. Okay. So now let's look at this third one, R1 tilde. So here we have the diagonal values to be equal to 1. All the values in the diagonal are 1. So reflexivity is satisfied. Let's look at symmetry. Here, let's write numbers so that you will not confuse. This is 1, 2, 3, 4, 5. Okay. So first we are looking at 1, 2, right? Let's take a different color. 1, 2 and 2, 1, both are same. So, okay. So then 1, 3 and 3, 1, both are same. 1, 4 and 4, 1 are same. 1, 5 and 5, 5 are also same. And then we'll go with this. 2, 3 and 3, 2 are same. 2, 4 and 4, 2 are same. 2, 5 and 5, 2 are same. Then let's go for 3. 3, 4 and 4, 3 are same. 3, 5 and 5, 3 are same. And finally, these two pairs are also same, right? Hence, the symmetry is also satisfied for this. So this particular relation matrix is also a fuzzy tolerance relation. Okay. So this is our last one. So I want you guys to tell me if this is a fuzzy tolerance matrix or not. Okay, I'll give you a minute or two. Is the fourth one a fuzzy tolerance relation or not? Yes. Yes, generally you are right. So it is a FTR. Right. So we have all the diagonal values to be 1. So it is a the reflexivity condition is satisfied, and then all the pairs in this way are also satisfied. So it is also satisfying the symmetry condition. So the reflexivity is satisfied. The symmetry is also satisfied, right? And hence we call this as an FTR. So all the FTRs we have seen in these examples. Yes, Yamuna, you're right. All the FTRs that we have seen in all the examples so far are E and R1, and the fourth one, let us just call it as A. Okay, R1 and A. So all these three relation matrices are FTRs. Okay, so fuzzy tolerance relation is done. Now we'll look at a different type of relation called as fuzzy equivalence relation. So fuzzy equivalence relation has three conditions, right? So the first two are nothing but what we have followed in tolerance, right? That is reflexivity and symmetry. So in a way, I can say that all the FTRs, that is the fuzzy tolerance relations, are FER as well, right? Oh, sorry, it should be the other way around. Thank you. All the FER are FTRs as well. Okay, because all the fuzzy relation equivalence relation, they have to satisfy reflexivity and symmetry, which is the main and the only things for FTRs, right? And hence all the fuzzy equivalence relations are also all fuzzy tolerance relations. Okay. So we have two conditions for these equivalence, these two, and the third one is called transitivity. So let us say we have x1 x-ray, and the membership value of x1 and x-ray, sorry, xi and x-ray is lambda 1, and the membership value for x-ray and xk is lambda 2, and for xi and xk is lambda. Okay, so it's basically like xi xj lambda 1 xj and xk is lambda 2, and when I'm picking up this and this xi and xk, the membership value is lambda. Okay, it should be such a way that lambda should be greater than whatever the minimum value is there in between x1 lambda 1 and lambda 2. Okay, so this is the third condition. So if this condition is satisfied, then we call uh, it as transitivity condition. Transitivity condition is satisfied. So if all the three conditions, reflexivity, symmetry, and transitivity are satisfied, then we call the given relation matrix as a fuzzy equivalence relation matrix. Okay, clear? Any questions? Is transitivity clear, or should I explain it again? Yeah, you can send a message. It's fine. I can see people typing. Hmm. Okay, great. Okay, thank you, Janani and Yamini. Okay, so let us do it with an example. So as you can see, this one, reflexivity, all the diagonal values are equal to 1, and hence it is satisfied. And then symmetry, all the pairs are also satisfied, right? The symmetry is also satisfied, reflexivity is satisfied. Now we have to look at transitivity. So let us take x um, 1, 2. So, let's take x 1, 2, and just let us say I, j, k are 1, 2, and 3. Okay. So x I j, you have to take x j k and x I k or something like that. Okay. So for now, let us take I equal to 1, j equal to 2, and k equal to 3. Okay. So x 1, 2 is nothing but 0.8, x 2, 3. Sorry, this is a bit more confusing. X1 comma x2. Okay. X1 comma x2 is 0.8. Then we will take xjk, that is 2 and 3, x2 comma x3. So x2 comma x3 is 0.4. And then we will take xik. So that is x1 comma xk. X1 comma xk is 0.4. Okay. K is 3. Hmm. Now, this is our lambda 1, this is our lambda 2, this is our lambda 1. The condition is that lambda should be greater than or equal to minimum of lambda 1 comma lambda 2. So the lambda is 0.4 greater than or equal to minimum of 0.8 comma 0.4. The minimum value here is 0.4. LHS size is equal to RHS size, which means that condition is satisfied. So like this, you do it with respect to different ijk values. So you can take ijk 1, 3, 2, 2, 1, 3, 2, 2, 1, like that. Like random values you can take, and you have to check for at least a couple of them, and then all these values should satisfy this one main condition, which is lambda is greater than or equal to minimum of lambda 1 comma lambda 2. So if that is satisfied, then we call it as a transitivity condition is satisfied. And when reflexivity, symmetry, and transitivity is satisfied, we call it as a fuzzy equivalence relation. Okay, clear so far? Okay. So this is again the same questions that we have seen earlier, right? So this one is not even a square matrix. So I apologize for keeping this here, but just remove the last one. Okay. So this itself is not following the reflexivity condition. So hence this is not. And the next one, O is also not. E is satisfying the first two conditions, that is reflexivity and symmetry, both are equal. So now we have to see for lambda 1, lambda 2, lambda 3. Okay, here since all the values are same, no matter what you take, it is going to be 1 greater than or equal to minimum of 1 comma 2, 1 comma 1, right? So which is going to be 1 equals 1, 1 greater than or equal to 1, which is equal. So which is true because both of them are equal. So this is going to be in fact TER, sorry, FER, fuzzy equivalence relation. Okay, so now let us look at this. So we all know that R1 is satisfying the first two conditions of reflexivity and symmetry. Now for transitivity, we'll see. We have how many values? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, we'll just do one, but you guys can go ahead and try out for different random values as well. Okay, so let us take ijk. Let's take some random 2, 4, and 5. Right. First, ij is x2 comma x4, which is equal to x2. X2 is this. x4 is this, so it is 0, and then take j and k, 4, x4, x5. So x4 is this, x5 is this, so the membership value is 0.5. And then we'll take x2 and x5. x2 is this, and x5 is 0.9. So it is equal to 0.9. So this is your lambda 1, this is your lambda 2, this is your lambda. So lambda should be greater than or equal to minimum of lambda 1 comma lambda 2, which is 0.9 greater than or equal to minimum of 0 comma 0.5, which is 0.9 is greater than 0, which is true. And hence, so like this, you do for a couple of values, okay? And then you can call this as a fuzzy equivalence relation. And the same way you can do for this as well, okay? You can randomly take some values and try it out yourself one after the other, okay? But I suggest doing it for all the pairs possible, and you'll get your answer, okay? Right. So that is the equivalence relation. And now we okay. Now let us look at this. So here, if we are taking, if we have two relations R and R, the same relations, and if you are taking the composition between them, then you'll get some value. So similarly, once you do multiple compositions for the same relation over and over again, then it is for n minus 1 values, then you write it as an R dash. So where n is a cardinal number. Okay, so this is let's go. Okay, so if I'm doing it three times, then it's R cube. R R O R O R. Okay, like that. Here we are doing it for n minus 1 times, where n is the cardinal number. Okay. Okay, here we have a relation matrix. Okay, R, and you let us take R square for this. So that is composition between R and R. Okay, okay, I can leave some space here, but anyways, I'll write it down. Sorry. Okay, so for R square, it is ROR. Let us take maximum composition. That is the easiest. Right? So this is just for my sake so that it will be easier for me to do multiplication sort. So we take this, so it is max of 1 intersection 1, comma, 0.8 intersection 0.8, comma, zero point 0.4 intersection 0.4. So max of 0.1, 0.8, 0.4, which is equal to 1, right? So okay, that is for 1. Another, you take this and this. Max of 1 intersection 0.8, zero point 0.8 intersection 1, and then 0.4 intersection 0.4. Okay. So this is max of 0 0.8, 0 0.8, 0 0.4, which is equal to 0. This is 1. This is the second element. Third element, you take for this and this. Okay. So it is max of 1, comma 0.4, 0.8, comma 0.8 intersection 0.4, 0.4 intersection 1. Right? Max of 0.4, comma 0.4, comma 0.4, which is equal to 0.4. Okay. Then the fourth element, we take this with this. So it's max of 0.8 intersection 1, comma 1 intersection 0.8, comma 0.4 intersection 0.4. So it's max of 0.8, comma 0.8, comma 0.4, which is equal to 0.8. Right? So like this, you do for all the values. Okay, you calculate for all the values, and so till so far I have written. So I'll just write. So this is 1, this is 0.8, this is 0.4, and this is 0.8. So similarly, just do for other elements as well. So once you do these things, find if this particular matrix is a fuzzy equivalent relation or not. Okay. If it is not a fuzzy relation equivalence, then go for R cube. Even if that is not a fuzzy equivalence relation, then go for R4. Okay. So when you do that, what happens is you get to the cardinality point as well. Just a second, there is some issue with the Wi-Fi. The LAN is working, but the Wi-Fi is not. So just give me a second until I figure it out and share my screen. Okay. Yeah. So I hope it's visible now. Okay. So that is how you do. So once you find R square, you check if the transitivity the all the three properties that we have discussed are followed. And you, in case if it is not followed, then you go for the next one, that is R cube. And then you go for R4, R5, like that. Okay, until and unless you find somewhere or the other that the transitivity property and all the other two properties also satisfies. Okay. Huh. And apart from all the properties that we have discussed, that is the reflexivity, symmetry, and the transitivity, there are two other properties, and they are called antisymmetric properties. So the first one is antisymmetric properties, and the second one is antireflexivity properties. Antireflexivity property is nothing but the opposite of the reflexivity property. Where in reflexivity property you have the membership values in the uh, diagonal space to be equal to 1, but whereas in this it is going to be 0. Okay, so this example that we have seen, this O, sorry, this O that we have seen, all the diagonal values are 0, so it is anti reflexivity property. Okay. Like that, we have anti-symmetric property. So anti-symmetric property is when the membership value of xi and xj is greater than 0, whereas for xj and xi is equal to 0. So it's like, let's say 1, 2, let's take one more, 3. Uh, Let us pick maybe 1, 2 and 2, 1. Okay. So 1, 2 should be greater than 0. Let us say 0.5. And ji, that is 2, 1, should be equal to 0. So this part will be 0. Similarly, that if we are taking 3, 1, okay, or 1, 3, let's take 1, 3. If 1, 3, that is this value is going to be some different greater than 0, maybe 0.4, whereas this is going to be 0. Similarly, this is already 0 for us. Okay. And here for 2, 3, maybe 0.7, and here it is 0. Let us say. So this is basically a matrix which follows both anti-symmetric property and anti-reflexivity property. The diagonals are equal to 0, this, and for anti-symmetry, so all these values are equal to 0, but whereas for the other ones, it's greater than 0. Okay. Apart from these, so the next, so that is where the NPTEL syllabus is done, like for this week. And apart from these, I have added a couple more composition operators apart from min, max, and max product. Sorry, max min proper, max min and max product compositions. So these are other types of composition operators in a similar way. So one is min max. So what you do is you take the maximum first, and then you take the minimum over um, x. X. And max max is when you do both max operations, and min min when you take both minimum operations, and then you have max average where you take max and then you take the average. So you add up these two and divide it by 2. So that is max average. And then you take sum product. So this is a bit different. Okay. So this is just to make you all aware that there are other type of composition operators apart from the two operators that are discussed in the class. Okay. So yeah. So with this, I'm done for today's work. Okay. So as discussed earlier, you can try the previous questions that we were doing. Yeah. So I hope you all have copied the questions when we were discussing. So you can go ahead and try to solve this question. So I'll leave this one on for another 10 minutes, and maybe till 7:13. I'll just keep the screen so that you'll have access to the questions. And at 7:13, I'll shift to the next problem so that you can do it by yourselves. So this is all simple math. So I'm not doing it over and over again. Okay. So yeah, any questions so far? Okay. So since there are no questions, so now I'll wait till 7:15 and you can do your questions. And at 7:30, sorry, 7:13, at 7:13, I'll shift to the next question and you can do the next question after this. Okay. So if you have any doubts in between, just drop it in the chat box and I'll answer. Okay. One second, Janani, I will just share it. Thank you so much, Reenu. Is it visible or should I just? Okay, Janani, just let me know once you're done copying this so that I can shift back to the questions.